We are live.
Should I start?
Yes, sir.
Good morning, everyone. At the outset, I want to thank Dr. Namrata, AOS, and especially Dr. Raji Raman for putting this webinar together on a very, very interesting and most needed uh, at this hour webinar for our understanding of what AI is. I think today we are in a very fascinating intersection of artificial intelligence and of ophthalmology, especially focusing on its transformative impact on eye care. As you all know, AI is really running into inroads into ophthalmology. It started with the diabetic retinopathy screening, and it's really making a big change. And it is important, as people say, AI is the new electricity. It's important we all gear up to understand what it is. I myself started working with AI, so-called AI. At that time, it was more of imaging or in 2007, and not until 2014 when Dr. Rajiv and me worked with Google to understand some AI parts to develop DR screening tools. And today we have that in use in real time. Today, AI helps to replace not just the simple activities, that repetitive tasks like grading of the images, but it is also helping in predicting, which you're hearing so many things about predicting your cardiac diseases by looking at retinal fundus photographs. AI can help making predictions using data, whether the patient with diabetes can develop diabetic retinopathy in future or not. You hear so much about these things coming up. It is important that we understand what it is. I recently saw an application called Anura, developed by a Canadian company, which just takes a smartphone photo of your face and reads the supposedly reading the blood vessels, and it is giving 24 different parameters of your body, including cardiac, your mental index, BMI, and so many other things. So it's very interesting. We are in a very, very interesting situation, but it is very important as care providers that we understand what AI can do going forward, because it is patients who are going to drive us to understand this better. Otherwise, we will be at a loss when patients ask us what these are all about. So I really, really want to thank Dr. Rajiv for putting this together, because at the core of AI applications, we have several key techniques which we don't understand, such as deep learning, natural language processing, LLM, transfer learning, and all that different stuff. And we also know AI has the potential in screening and eye diagnosis to monitor disease progression for personalized treatment plans that are coming up. AI can assist clinicians in deciding whether to intervene or to adjust treatment strategies. In fact, recently I was working on an application that summarizes. We have patients who have been having 100 visits, 150 visits as retina surgeons, and it is very difficult to understand, go through the entire, but these AI tools can summarize and give it in graphical forms to understand how the patient did for your treatments in the past. So these are very, very interesting factors that are coming up. So we need to understand how this is possible. And today, Dr. Raji Raman, on behalf of AIOSSC, has managed to get the time of some hardcore AI experts in the field of artificial intelligence to give us the basics of AI. And I want to extend my gratitude to all the speakers for taking their Sunday time to enlighten us about AI. I'd also like to thank again Dr. Raji Raman for organizing this wonderful webinar, and now request him to introduce the speakers for this important webinar. Over to you, Dr. Rajiv.
Thank you. Thank you, Dr. Kim. Uh, as you rightly said, the aim of this webinar is the ophthalmologist should get equipped with the basic understanding of the terminologies, what these terms are, and how they have been transferred, how they have been applied in retinal diseases and ophthalmology, and to make our life more easy. So I won't waste time, but let's start with the first talk, and I would like to invite Professor B. Uma Shankar. Professor Uma Shankar is a professor and head of machine learning, a machine intelligence unit at Indian Statistical Institute in Calcutta. And his research areas are mainly related to AI, pattern recognition, the machine learning, and image processing. And he'll be talking to us on AI terminologies which are there and understanding AI basically by you, what these terminologies actually mean. Thank you, sir.
Good morning, everybody. I'm Uma Shankar from Indian Statistical Institute. I will be talking about AI terminologies. So let me start from the very beginning. That is, it is said that John McCarthy, a mathematics professor at Dartmouth College, coined the term artificial intelligence during the 1956 conference. As we all know, humans are the most intelligent species on Earth. The initial understanding was that if we cannot distinguish between a human and a computer responding to questions, then we may call that computer is intelligent. This is also known as the Turing test. In simple words, Turing test is a method of inquiring into AI systems for determining whether or not a computer is capable of thinking like a human being. Therefore, we can say that a group of technologies known as artificial intelligence allow computer to simulate cognitive processes like learning, reasoning, and problem solving, just like humans do. Artificial intelligence mimics human intellect through data, algorithms, and computer power. The current understanding of AI is the development, use, and maintenance of computing systems that can imitate particular type of human intelligence. These days, this area of computer science is focused on creating machine learning models and algorithms that can analyze massive amounts of data on their own to get insights and make decisions. An important goal of this research field is to investigate how technology can be used to carry out cognitive tasks that humans find tedious or challenging. Although AI is treated as a disruptive technology, this technology will become normalized and integrated into our everyday life in due course of time. Deep learning is a subset of machine learning. Actually, deep learning also can be called a machine learning. We basically there are three ways that we can do this. One is unsupervised learning, then supervised learning, and reinforcement learning. But all this learning process uses data. So data is at the center of AI. Data can be small or big data. The main difference between big data and small data are volume, variety, velocity, and structure. The general term big data refers to collection of unstructured data from a wide range of sources. Small data, on the other hand, is well organized, structured, concise, simple to understand, and easy to comprehend. An organization or application can benefit from both big or small data, since they both can influence the net result. Statistical analysis of data is also called data science or statistical data science. Now, question is, what is learning? Education is not the learning of facts, but the training of the mind to think. If you have any doubt about what future computers can do, some idea you can get from the Yam Leaken's lecture, uh, which can give some insight into the thinking of computers. Model in AI refers to a mathematical representation or framework created to simulate or emulate some aspect of the real world or from a problem domain. AI models are designed to learn from data, make prediction, or make decision based on the specific algorithm. Below given are some examples of models. An algorithm is a set of instructions or rules followed by a computer to solve a particular problem or perform a specific task. Algorithms are essential to the operation of AI systems as they power operations including data processing, learning, optimization, prediction, adaptability, and ethical consideration. Understanding and developing Effective algorithms are key to advancing the capabilities and responsible deployment of AI. From the technical and mathematical standpoint, machine learning processes focuses on processing a collection of input-output pair for a specific function and predicting the output for new inputs, also known as generalization. Some examples are given below. Deep learning is a subset of machine learning that uses lots of layered neural networks called deep neural networks to simulate the complex decision making power of the human brain. Some form of deep learning powers most of the artificial intelligence application in our lives today. Some examples are given like CNN, RNN, transformer, and fully connected deep neural networks. The workflow of machine learning model are as follows. The model is trained on data to learn underlying patterns. The algorithm identifies patterns to develop a predictive function. The model takes input and predicts the output. Model's performance is further evaluated on the test or unseen data sets. Evaluation of model is very important using relevant measures. Reinforced learning is a machine learning technique that trains software to make decision to achieve the most optimal result. It mimics the trial and error learning process that humans use to achieve their goal. The software learns to make decision by increasing with an environment and receiving a feedback in the form of rewards or penalties. The aim is for the agent to learn the optimal action to take in order to maximize the cumulative reward over time. Commonly used in robotics, games, autonomous systems, etc. Computer vision is a field of AI that involves enabling machines to interpret and understand the visual world, images, videos, and other visual input. It is used in a variety of applications, including medical image analysis, automatic inspection, detection, image recognition, classification, segmentation, registration, etc. Computer vision tasks include method for acquiring, processing, analyzing, understanding digital images, and the extraction of high-dimensional data from the real world in order to produce numerical or symbolic information, drawing inferences from the images or prediction. Generative AI refers to a subset of AI techniques that involve the generation of new content, such as images, music, text, or even entire virtual worlds. Unlike other forms of AI that focuses on tasks like classification and prediction, generative AI focuses on the creation of new original content. Generative AI models are trained on large data sets and learn the underlying patterns and create structures in the data. They then use this learned knowledge to generate new content that is similar to the training data. One popular approach in generative AI is the use of generative adversarial network. Large language model. Large language model is an AI system that can recognize and produce human language through machine learning. A bot is a computer program that can perform tasks automatically, while a chatbot is a type of bot that can have a conversation with user. ChatGPT is a machine learning powered AI chatbot that analyzes data and produces responses to queries and commands from users that seem human. To improve their ability to react to user requests, large learning models undergo extensive training using vast amount of data, including text from the internet. They have several task performing abilities, including text generation, sentiment analysis, information retrieval, code generation, chatbots, translation, answering questions. Some good examples are now every day you encounter are Gemini, Microsoft Copilot, Meta AI, etc. Data leak occurs when you are not careful to distinguish training data from validation data. Leakage is often subtle and indirect, making it hard to detect and eliminate. Leakage can cause a statistician or a modeler to select a suboptimal model, which could be outperformed by a leakage free model. Explainable AI. Explainability refers to techniques that make AI model decisions and prediction interpretable and understandable to human. When it is a black box model, you may ask questions like why this prediction, why not another prediction, when does the AI model succeed, when does the AI model fails, how to correct an error, when can I trust my AI models. All these answers can be find in white box models. Particularly, I can trust my AI model when it is fair, reliable, and can be explained, accounted for, and is secure. Some good examples are CAM, GradCam, Lime, Sharp, and Occlusion. Ethics. With AI playing an increasingly important role in our various aspects of society, AI ethics has become a crucial consideration. This field addresses ethical concerns surrounding AI development, deployment, and use, including uses related to bias, fairness, transparency, accountability, and privacy. Deepfake is an AI generated image, audio, video depicting fake events. It uses powerful machine learning and AI to manipulate or create deceiving content, sometimes that can be problematic. Conclusion. It is increasingly being integrated into various industries and applications, from healthcare and finance to transportation and entertainment. As AI technology continues to advance, its potential to transform industries, improve efficiency, solve complex problems is becoming more apparent. Nevertheless, ethical consideration, transparency, and regulations are crucial aspects to address, and AI adaptation continues to grow. By understanding these key terms, we can keep abreast of the latest AI trends and concepts and position ourselves for success in the rapidly evolving world of AI. These are some relevant experience references. The first one is actually regularly updated by ophthalmologists. It is available at iWiki. Thank you. Any queries can be sent to my email address.
Thank you. Thank you, sir. Welcome, Dr. Namrata.
Thank you, Dr. Rajiv. Thank you so much.
So nicely you could present what are the various terminologies. I wanted to know, like in medicine, there are many of these terminologies or classifications are universal. Like you call the same thing here or somewhere else, it is same. Is it same with AI terminologies? They are universal across various industries also, like healthcare versus some other application, or is there any difference as far as the basic terminologies are concerned?
No. Terminologies
Terminology will be the same.
will be same. The difference comes where the application is. See, domain expert interprets it in a different way. Just now I said that explainable AI becoming popular because of that only. Because you want to answer those questions. I mean, I just you will say my system is giving this result is not sufficient.
Correct, correct, correct.
Can I ask a question?
Please,
I
please.
know it is not going to be very, a very layman type of a question, but I wanted to understand that is AI, given the fact that so much of data goes into generating any kind of a module, is AI amenable to manipulation at a data which is to be individually generated? I don't know if I'm putting it correct or not.
Yes. All these things are part of big data.
Okay.
Every question that you are thinking of in your mind, the answer is there. I mean, people can play with the data, destroy, generate false information. That is the big challenge of today.
Sure. I think we'll go to the next session, next part of the webinar, which is on machine learning. I would like to invite Dr. Sundareshan Raman, very good friend and collaborator, who is associate professor in Department of Computer Science and Information Systems at BITS Pilani. And he has been working on medical applications, and I would say more so in ophthalmology for last 3 years, 3 to 4 years. We have published a couple of stuff together. Real master in looking at how, and I can never forget, he did a course when there was the COVID time, and he was stuck in Chennai. So he did a course on Python. He did a course on image processing, online lectures, about 20, 30 of them. Excellent teacher. And I would like him to talk about the basic concepts of machine learning. Dr. Sundaresh. You want us to put the video and then you can answer the questions. You are muted. Dr. Sundaresh?
Yes, sir. So thank you for your introduction, and I'm very thankful to Dr. Rajiv Raman for giving me this opportunity, and also to Professor Namrata Sharma for allowing me to talk about machine learning today. So I was thinking I can just present my slides and then...
Perfect.
Okay. I hope my slides are visible.
Yeah.
Just a second. I'm quite new to Zoom. I mean, not generally use Google Meet. I'm just trying to get the controls.
It looks okay.
It looks fine.
It looks fine to us.
Okay. Just
Doctor, you can click on the screen and start the slide. The slide should move. Just click on the screen. Yeah, all good. All good.
All right. So, so today we'll talk about machine learning. First, I'll give a brief context to the machine learning, where it is. Professor Uma Shankar already gave a very beautiful, definitions of the different terminologies. So some of them might be overlapping. We'll also look into some basic applications of machine learning and what exactly is machine learning and what is the need for having a learning algorithm. So we'll also look into what is meant by an algorithm and what is a learning algorithm and what are the different types of machine learning and some examples. And finally, some of the steps that are required to build an ML model. So artificial intelligence began in the 1950s, and it created initial excitement, but it kind of subsided until machine learning began to flourish in around 80s and 90s. So machine learning is a subset of AI. And even more so, deep learning, which is still a smaller subset of machine learning, and it began to create such tremendous breakthroughs. So artificial intelligence, all of these are basically talking about algorithms. So we will talk about what is an algorithm and what is a learning algorithm also. So AI refers to algorithms that mimic the intelligence of the humans, whereas machine learning also corresponds to algorithm, but it is very good in learning from data. And it makes well-informed decisions using the mathematical models it learns. And it makes use of human extracted features. Like, so the data is not directly fed into the algorithm, but one needs to have a domain knowledge of what we are working and extract suitable representations which can be fed into the algorithm. Whereas deep learning, which is a subset of machine learning, it learns those features automatically, without having to explicitly extract them. So it learns these features in a progressive fashion. So these are some of the applications of machine learning, and there are many more to it. Like, it can be used for recognizing faces. It can be used for aiding, in augmented reality applications related to users' preferences, etc. Can be used in chatbots, which are nothing but programs, that simulate human-like conversations with an end user. And there is no need of mention of how machine learning could be used in healthcare for identifying a specific stage of a disease, or to compute the probability a person might get a specific disease in, say, 4 years from now. Can be used in driver surveillance, like to detect if a driver has fallen asleep or not. Or it could be as simple as spam detection. So there is an incoming email, we want to automatically classify into a spam or a non-spam. So what exactly is machine learning? So it refers to the application and science of algorithms that make sense of data. Or in other words, you can say it as a study of computer algorithms that improves automatically with experience. So that is what we mean by machine learning. Let's take a simple example. We have different patients, predictor variables, different features, and those are fed into a classifier model. We may call by different names like a machine learning system or learning algorithm or a model. All these are basically refers to mathematical equations or formulations, which when learned can be used to predict or make a prediction. And so the output here is to identify whether a person based on those variables has diabetes or not. So obviously we cannot program to give, we cannot give explicit instruction to the algorithm, right? Because it depends a lot on the combination of different variables. So we cannot give explicitly the instruction just like we do in a typical computer programming. So today we have huge amounts of data, and we have, like Professor Uma Shankar was telling, we have structured data, unstructured data, and with the help of self-learning algorithms, which machine learning provides us with, we can convert this data into knowledge. So what exactly do we mean by an algorithm? An algorithm is simply a set of rules or instructions to solve a specific problem. For example, we can come up with an algorithm for creating a recipe. If you want to bake a cake, we can create an algorithm for it. It would be as simple as heat the oven to a specific temperature, gather all the ingredients, mix it thoroughly in a bowl, pour the mixture into a baking pan, bake it in the oven for a specific duration, and then repeat or in a loop, keep on baking for 5 minutes more until you see that the cake is ready. And finally, you pull it on a rack before cutting it. So this is an algorithm for creating or for baking a cake. Here is another algorithm, which is to determine if a person can cast vote or not. So the input is age of the person, and the output is whether the person can vote or not. And it is as simple as if the age is greater than or equal to 18, the person can vote. Vote equal to yes, otherwise vote equal to no. So we see here this algorithm is extremely simple, but there is no learning involved here. It's just a set of rules. It's just one rule. If the age is greater than or equal to 18, you vote, you can vote. Otherwise, you cannot vote. Let's look at another example. What if the input is an employee image capture, right? And the output is we want to mark the attendance for that employee in an organization. So now the question is, what can we instruct? How do we instruct? We don't know the identity of the person because this is in real time, the image is getting captured, right? So we cannot explicitly program here, and hence there is a great need for learning algorithm, an algorithm which can learn based on the data that it is provided with, and it can use that learned model to automatically or to make a suitable prediction for an unseen data. So what exactly is learning? So Tom Mitchell, he's the founder of the machine learning laboratory at CMU, the first ML lab in the world. He defines learning as follows. A computer program learns from experience E with respect to a specific task and some performance measure P. If the performance for the task D, as measured by the measure P, improves with the experience E. That is, before the experience and after the experience, has there been an improvement in the performance? And what is the experience here in terms of machine learning? The experience is through data, because as Professor Uma Shankar was telling, center of AI is data. It's all, everything is there in the data. So again, I want to mention one point that although we are talking about machine learning, actually machines don't learn. I mean, it looks opposing, but why is that machines don't learn? Like, for example, let's take a simple example. If suppose you want to learn how to play a video game, and you're given the screen, a straight screen, and you play at it, and in some time you become very expert in it. And suppose you are given a slightly tilted version of the screen, you still probably would be doing very well. But on the other hand, if suppose a machine is trained to play and it's given the straight screen, unless it is also trained for the rotated version, it will give a completely different result. So the learning that we define here is very different from what we refer to as learning in our day-to-day lives. So the learning here is it's all based on the data. So it cannot go beyond the data. Based on what it has seen, it has just in an abstract mathematical formulation, you create a model, and when a new input comes, and it works well if it is from the same statistical distribution. So in the case of an email spam filter application, the task could be to label the email as spam or not spam. The experience could be a corpus of emails in a suitable representation with the labels. The performance measure could be the fraction of emails correctly labeled as spam or not spam. And the learning is the ability to perform the task. There is another important aspect of machine learning, which is the feature extraction. It's also called feature engineering. So, and that depends on the domain in which we are working. So one needs to have a domain knowledge, like the data that we acquire cannot be directly fed into the learning algorithms. We have to extract, identify the most discriminating factors, at least potentially discriminating factors, which we call as features. Like for example, if you want to know if your input email is a spam or not, how do we find? We will probably look into the email, the name of the sender. It seems a little suspicious, not the usual ones. Maybe the length of the message, the number of hyperlinks, or the number of exclamation points. All these could be, and even more, could be the features for this particular application. So from the input is the emails, and we extract all these features, and which we feed into the machine learning algorithms along with the labels. And then it can, for a new test email, it can again compute these features, and based on the model it has learned, it can predict as spam or not spam. So there are three types of machine learning algorithms. One is called the supervised learning, in which there is labeled data. That means, say, if we have 10,000 emails, for each of those examples, we have the corresponding label as spam or not spam. It could be in terms of 0 or 1, true or false, whatever. And here there is a direct feedback because we have the labels, and it can be used to predict the outcome or the future. There is another type of learning called as unsupervised learning. So there is no label or target. And obviously there is no feedback here. So what is this? Then how does it learn? So it is more or less like an exploratory analysis. The idea is to find the hidden structures in the data. We will look at some example of unsupervised learning. And then there is reinforcement learning, where there is an agent that interacts with the environment, and based on the action, one gets reward, either positive or negative. The idea is to learn a series of actions, and it maximizes the cumulative rewards. So in supervised learning, we see here, so there is the machine learning algorithm. There are different types of different machine learning algorithms. We are not going into the details of those algorithms because of lack of time, but we will just keep it as this, we'll call it as a machine learning algorithm right now. It is supervised because we also have the labels associated with the training data. And once the mathematical formulae are learned, it becomes a predictive model. When a new or the test data comes, it can make a nice prediction. One example is regression, which is a very simple but powerful machine learning technique, supervised learning technique. So it learns from the examples to predict the continuous values. So basically it models the relationship between the independent variables, the predictors, and the response or the target variables. And it allows to estimate or predict the numerical values. It basically minimizes the sum of the squares of the distance between those points and the fitted line. Here is an example. Suppose you want to predict the math SAT scores of students, and we assume there is a relationship between the time spent studying for the exam and the final scores. So on the x-axis, you have the time spent. On the y-axis, you have the scores, which is normalized. And there are 5 examples of students and their scores. and we have fitted a line, and the mathematical formula learned is y equal to 4.96x minus 18.98. Now, you increase the data points, you see the line is changing. We're increasing in 15, 20, 25, 30, 35, 40, and there are 50 data points, and this is, you see the equation has changed. So which means the model has changed. It has learned better. Now, if a new student comes, like if you know the X value, we say if it is 9 hours, then you know the score as 20. So this is an example of supervised learning, the case of regression. Another example, another type of supervised learning could be classification task, which is again a subset of supervised learning, where the goal is to predict the categorical class labels of new instances based on past observations. Again, it learns from the data to improve the accuracy in class assignments. Like you could consider this, the plus as on the figure as the spam emails, and then minus as the non-spam. X1 and X2 could be the top two features, which could be the number of exclamation points or length of the message and so on. Here's another example of classification. You have brain tumor. We have listed down 4 types: glioma, meningioma, no tumor in pituitary. And we want to now, given a new MRI scan, we want to classify into one of these 4 buckets. So the feature engineering is we need to extract some features which can be fed into the algorithm. And these are the gray level co-occurrence matrix, which we call as GLCM contrast, and the compactness index. So these 2 numbers are created or extracted or handcrafted for each of these images. And along with the labels, it is fed into the ML model. And this is called as the training. The model, it learns the equation, it becomes better and better. And once we are happy with the training, now it can be used for any test data. That is, when an image comes, you extract the same features and then use the equations that have been learned, which we call as the ML model, and make a prediction. Now it says as pituitary. Now we go on to the next type of learning, which is the unsupervised learning. Here it is learning from an unlabeled data, and obviously there is no right or wrong answers. The idea is to discover some structures inherent in the data, some patterns, etc. And there is no supervision during the learning process. Let's look at a simple example to understand unsupervised learning. Suppose there is a retail company that is trying to understand the purchasing behaviors of the customers. And obviously there are no predefined labels, but the company simply has some data, 4 types of data. One is the total amount spent, the frequency of purchases of the customer, the types of the products bought, and the demographics of the customers. These are the only information. We don't have any labels as regarding a high spender, etc. Now, how can we make use of machine learning here? We can make use of some techniques in unsupervised learning. For example, if we use clustering, the company can group the customers with similar purchasing patterns into different segments, like a frequent shopper, high value customers, discount seekers, and occasional shoppers. So there is one specific algorithm called as k-means clustering, which is an unsupervised technique. And by using that, in fact, only these 2 features, it is able to clearly cluster these 4 different categories as occasional shoppers, frequent shoppers, discount seekers, etc. So this is an example of unsupervised learning where there are no predefined labels. And then finally, there is reinforcement learning, where an agent interacts with the environment to make decisions and learns through feedback, which comes in the form of rewards or penalties. And the idea is to maximize the cumulative rewards over time. And it basically learns through trial and error without any explicit instructions. So finally, let's now look into some of the different steps that are involved to build a machine learning model. First of all, there is data collection, which is very, very important because without data, the machine cannot learn, right? So after the data is collected, it is to be pre-processed. That means some corruption is there in the data, some data is missing, all those have to be addressed. And then we have to select the right ML model, whether we are doing regression or classification, or even within classification, there could be, say, logistic regression. It's one type of one algorithm. It could be a decision tree or an XGBoost, a cascade forest, so many different algorithms are there. So we have to choose the right one. So generally handful of them are used, and we then train it. So that is basically the mathematical formulas are learned, and then we evaluate the performance of the model on an unseen data. And then there's also something called as tuning and optimizing the model. That means there are certain parameters called hyperparameters, which are set aside as constant even before the training begins. For example, the learning rate or the regularization that is used. So those could be fine-tuned, and certain optimizers could be used for optimizing the model. And finally, it is deployed after choosing the best model. So there is much more to it in all of these stages. We just looked at the very high level picture of what are the different steps involved in machine learning. So with this, we stop here. Thank you very much.
Thank you. Thank you, Dr. Sundaresan. We'll continue with the next talk and then have a discussion. So the next talk is by Mr. Abhishek Vyas. He's assistant professor in the Department of Electronics and Communication Engineering at Thapar Institute of Engineering and Technology in Patiala, Punjab. And Abhishek has been student of Dr. Sundaresan Raman. I've been fortunate enough to co-guide his PhD. And he has been working extensively on these machine learning models for retinal application. So he will now share an example how it can be used for a retinal case. Abhishek, please. Shall we put the video, or you would like to present it directly? You are muted.
I will present it, sir.
Okay.
Is my screen visible?
Yeah, it is visible.
Morning, everyone. Thank you. I thank Dr. Rajiv Raman, sir, for giving me this opportunity to present this example of application of machine learning in retinal disease detection. So I will be talking about diabetic retinopathy, which you all know is a complication of diabetes.
Abhishek, you have to be a little louder because we can't hear.
Just a second.
Dr. Abhishek, you are not audible.
I think we'll play the slides. We have a video. We can do that. You can unshare and then join for the discussion.
People now.
Yes, you are audible, Doctor. We can try once. Can you hello, Dr. Abhishek?
Yes.
Can you please continue? If there is any problem, then we'll stop.
Okay, I will continue. So diabetic retinopathy is caused due to the complication of diabetes mellitus, and which damages the blood vessels in the retina. If not treated for a longer time, it will cause blindness. So our objective is to apply machine learning algorithms on clinical risk factors and predict the presence of DR using the structured data of risk factors which we are having. So we collected a data set of Ascent Dreams data set, which is a data set prepared by Shankar Netralaya and is collected from a population-based cross-sectional study conducted in South India to estimate the prevalence of DR in urban Indian population, which is older than 40 years. We have taken some risk factors for this data set. These are the risk factors: age, gender, diabetic status. Total 20 risk factors we have taken, and our objective is to predict the likelihood of multi-class DR using these clinical features. In this data set, we have these features in an Excel sheet, and the grading of DR also we are having for each patient. The DR grading is based on multi-class DR, where 0 stands for no DR, 1 stands for mild DR, 2 stands for moderate DR, 3 stands for severe DR, and 4 stands for proliferative DR. Now, in order to give this data set to a machine learning model, we need to pre-process it. So we apply pre-processing. So the first thing in pre-processing, if we have missing values in the data set or some values are absent, then we handle them by imputing these values with mean or median of the remaining values. Then we can also apply feature selection. We can have a subset of more important features. We have taken 20 features. We can take 10 or 15 more important features to for feeding this features to our machine learning model. We can do feature selection also, but here I have used all the 20 features. Then we divide the data set into training and test data sets. Training data set, we have taken 80% of the data set as training data set and 20% we will be testing our ML model. So for one new instance or record of the patient, we will predict if he is having DR of which class. So I am using a supervised machine learning model, which is called decision tree. Supervised machine learning model, as explained by Dr. Sundareshan, is basically it takes the data as input. We train this decision tree on that data, and then we take a new sample, and then we know the prediction. So I will just explain this. Just go through this table. This is a data or an Excel sheet, you can say, with 3 features and 5 patients, where the first feature is HbA1c level, second feature is duration of diabetes, and the third feature is blood pressure. And the prediction is DR prediction, which is given to us the true label, DR positive or DR negative. Okay. So our outcome of this decision tree is, which it will predict based on its model, that the person is having a new person when entered into the decision tree will have DR positive or DR negative. So when we give this data set of 5 patients, a tree will be drawn similar to this. So for first patient, if we input this first patient, HbA1c level is high, then it will ask if HbA1c level is high. If it is high only, so it will say yes. So it will predict, classify as DR positive directly. So basically it will take one by one these features and it will try to classify. If he is able to classify directly, then it will directly say DR positive or DR negative. Otherwise, it will go on the next feature and try to ask some questions. So using this, just a second. If we go on this second patient, which is having HbA1c as low, so it will ask the question, is duration of diabetes long? It is long. So it will just say directly it is DR positive. If we go with the third patient, low, short, and high. This is low, it goes over here, duration of diabetes is long, then it is also short, then it will ask if blood pressure is high. If blood pressure is high, it will classify as DR positive. If we go to the fourth patient, low, short, and low, come here, HbA1c is low, then duration of diabetes is also short, then blood pressure is also low, then it will classify as DR negative. So seeing this patient of 5 data, it will build this decision tree. And then if a new patient is entered, for example, we take a new patient as this third one from the test data. I am just taking an example. Now, if we take this new patient, first HbA1c level, it will check it is low. So it will ask, is duration of diabetes long? It is saying short. Then it will again say, is blood pressure high? The blood pressure is high. Then it will classify as DR positive. If HbA1c is high at the first instant, then it will directly say classify it as DR positive. It will not check the other features. In this way, we built a decision tree using supervised learning technique. Now we have trained our model, decision tree model, on the selected features, or we have taken 20 features, and on this data set, we totally, they just gave this example of data set of 5 patients, but in this work, I have taken a data set of 30,000 patients of Ascent Dreams data set. So how to evaluate this decision tree model, how it is performing good or bad? We have this metric, one metric as accuracy, which is defined as the division of number of correct predictions divided by the number of total predictions. And what I got using this decision tree on this 30,000 data of SN dreams, I achieved an accuracy in predicting DR classification of 88%. So how to basically do this work of building a machine learning model? This is the way. We load the SN dream dataset, including the features, then we pre-process them, then we split the data into training and testing sets, then we train the decision tree model using the clinical features we are having like HbA1c, duration of diabetes, etc., age, gender, and then we evaluate the performance using some metrics. I am just showing one metric, we can have other metrics also. And conclusion and future direction is this, that decision tree provide an interpretable way to predict diabetic retinopathy using clinical data. Unlike very high level deep learning models, decision trees don't require large data sets and they are computationally efficient. However, they may not generalize well to unseen data, especially if tree becomes too complex. So the further improvement is using XGBoost, which is called extreme gradient boosting, which is a powerful ensemble machine learning model which builds multiple decision trees sequentially. So instead of one decision tree, they will have multiple decision trees. Each decision tree will aim to correct the errors of the previous ones. So this XGBoost is well suited for structured data sets like our case of diabetic retinopathy having clinical features. When I used this XGBoost for this work, I got a test accuracy of 97%. The accuracy I am mentioning here is on the test data which is kept aside and is unseen to the model. So you can just see the difference between decision tree 88% test accuracy and XGBoost 97% test accuracy because it is a combination of many decision trees. Okay. Thank you all for your kind attention. Any questions are invited.
Thank you, Abhishek. So we looked into terminologies, then we went into machine learning, and now Dr. Sundareshan very nicely talked about the three methods of machine learning, and one of them, which is supervised, Abhishek nicely told us how he could apply this supervised machine learning technique to detect diabetic retinopathy presence or absence just through the risk factors. So here we are. So as physicians, as ophthalmologists, we know that to detect retinopathy, you need retinal images. But if you have a good amount of data which has research, all the risk factors, we can actually come out with what is the risk of that person having retinopathy. Any questions anybody else has with them? Otherwise, we'll go to the next one. Dr. Namrata, anything you want to add?
Again, I just want to ask something. Abhishek very nicely showed a diagnostic model, but I'm sure, again, in layman terminology, there must be treatment models also, that when you treat, what is the prognosis? So I'm sure that is going to be a more complex model. So in diabetic retinopathy, are we there?
Yeah, we are there to some extent about anti-VEGF treatment. We have been working and exactly the machine learning models. And I think from Zeiss, we have here, do we have, yeah, so Raghu is there. And we have worked with Zeiss on the AI model or the machine learning model, actually, exactly what you said, the supervised, to tell us what is the response of an anti-VEGF, whether it would be a responder, partly responder, or a poor responder. And our work used similar algorithms to find out a responder. There, it's not only the data from the metadata like the risk factor, but we added image data too. I think we will go to the next module, and I would like to invite Dr. Kaveri Thakur. Am I correct in the sequence? I think. Well, yeah. Hi, Dr. Kaveri. So,
Hi, Dr.
Dr. Kaveri Thakur is an assistant professor of ophthalmic sciences at Columbia University, and she heads the Thakur Artificial Intelligence for Vision Sciences, the AI4VS lab. And I was last year, I think similar time I was in US and I met her. Great work, and I was part of her the first trial which she was doing, trying to see how OCT. So it's a very exciting work, trying to create a medical expert AI team for eye diseases detection, which is driven by expert gaze data rather than, so it's a totally different concept. Rather than using the information from the data which is coming, we know that our eyes look at the things what we want to, like you show a OCT, expert will look at the lesions to diagnose what exactly is the disease. And Dr. Kaveri has made these algorithms where just by how the expert looks at these lesions, she can develop an AI algorithm. Welcome, Dr. Kaveri. Thanks for joining despite of a little odd time. Thank you very much. Shall we play our slides or you would like to talk?
Maybe we can go ahead and play my
Yeah.
slides. I'll do things a little bit just to change things around a little bit since it is very late. And since I have that.
Viraj, can you play the...
I don't think we can hear anything though.
No, it has not started. Volume. Has it started?
If it's an issue, I can
It should. I think you have to optimize for the audio when you present it. When you share the screen, unshare it. And when you are sharing the screen, there is a slot called as optimize for audio and video. You need to tick both of them. Then only the sound will come properly. You want me to share? I can do it.
Yeah, actually, I wasn't sharing. I don't know who was sharing.
No, Viraj is sharing.
Sorry. Oh, you're okay.
Viraj,
would you like me to share or?
Viraj, you want to share again or shall I try?
I'm happy to today my towards deep learning from medical imaging, specifically for ophthalmology. So I'll be talking about how we are developing an interpretable and portable, or basically trustworthy medical expert AI team for eye disease detection. So in my lab, we seek to enable the widespread clinical translation of AI in the ophthalmic clinic by achieving these three key thrust areas: robustness, interpretability, and portability. So towards robustness, we seek to develop algorithms that are generalizable to data collected from multiple locations and that can not only detect disease, but also determine when disease is progressing. Towards interpretability, we develop algorithms whose mechanisms are explainable and whose logic is clinically valid. And towards portability,
let me put it.
I think it's the second one in
This
the
one?
list.
Yeah.
Yes.
Yeah. Can you see the screen?
Yes.
Yeah, yes, we can see the screen.
I don't mind. I can just present. Then I can also tailor the timing because I realize our timing is getting short. So, because I don't think we can hear anything still.
Oh, you're not able to hear?
Yeah.
No.
Okay, then you present it. I think that's the best thing.
Okay. Okay.
Sorry.
No worries. Thank you for the opportunity, and I'll try and keep it to time. But yeah, so I lead this AI for VS Lab, and specifically I'll talk today about our goal towards developing a trustworthy medical expert AI team, specifically by making deep learning models that are more interpretable and portable for eye disease detection. So the method in which we seek to do that is by actually enabling widespread clinical translation of AI algorithms. And so we have three key thrust areas that we try to tackle to achieve this. So that is making models that are robust, meaning that they can be generalizable to data collected from multiple locations. Making sure that the models not only can detect disease, but also detect the progression of disease. Towards interpretability, we seek to develop models whose mechanisms are explainable and whose logic is clinically valid. And towards portability, we seek to develop models that are low cost and accessible and also interoperable across data of varying quality or data from multiple manufacturers, with the overall goal of creating a medical expert AI team that's hopefully better than the sum of its parts. So today I'll focus specifically on a couple of projects towards enabling interpretability and portability. So towards interpretability, as Dr. Rajiv was mentioning, we rely on the eye movements of clinicians. So in order to show how we integrate eye movements into AI training, let me give a little bit of background into large language models, since we take some analogy and inspiration from large language models like ChatGPT and the transformers, which are their backbone. So in transformers, there are two key concepts that are critical for their function. One is the concept of positional embedding. So in the language domain, where we can think of a sentence, and the sentence is composed of words or tokens, the positional embedding refers to the relative ordering of the words. So just the order of one word coming after the other, whereas self-attention refers to the context surrounding a word and the relative strength of association between any word and every other word in the sentence. So for example, the words chasing and criminal would have very high strength of association because of their common occurrence in the English language, as opposed to something like chasing and a tree. So similarly, if we now take these concepts to the visual domain, we have something called a vision transformer. And so instead of breaking a sentence into words, we would actually break an image into patches. And so now the positional embeddings refers to the relative ordering of the patches. So for example, top to bottom, left to right. And the self-attention refers to the relative strength of association between any two patches towards the final classification of this image as a cat, as opposed to in this case, where it's the goal was to predict the next word in the sentence. Here we're trying to classify the whole image into its class. So the strength of association between any two patches. So for example, here the cat's ears and paws would have much higher self-attention compared to, for example, this random patch just containing the sofa. So how do we actually use that and incorporate eye tracking to actually augment vision transformers? So first, we actually collect the eye tracking data of ophthalmologists. For example, here is our residency program director at Columbia wearing a head-mounted eye tracker. And he's looking at an OCT report where you can see the blue patches here actually show the regions that he was fixating on an OCT report towards detecting glaucoma. And here's another example where where the heat map is showing the regions fixated towards detecting retinal pathologies like AMD. So we take now these, how do we take these eye movements and actually then modify the positional embedding and self-attention of a vision transformer? So we do it in two key ways. So towards modifying the positional embeddings, instead of the inherent image structure top to bottom, left to right, we actually force the model to learn the gaze trajectory of the doctors as they view the image. So much like we might learn the grammar of a language, we learn specifically the patches that a doctor fixates in the order in which they fixate. And so in that process, we tremendously improve the efficiency of the model, because as you can notice, even from just these images, the doctor only looks at like 10% of the image to make their decision. So we call this a fixation order informed vision transformer, or FOI-VIT. In contrast, for the modifying the self-attention, we actually try to align the AI's inherent self-attention or strength of association between patches with the expert's eye movement attention, so the regions that they actually fixate most. And in this process, we seek to hopefully not only train the AI where the doctor looks, but potentially also show the doctor relevant regions that the AI has pointed out that maybe even experts might not have thought to look at. And so we call this ophthalmologist gaze augmented vision transformer, or OGA-VIT. So just to make that a bit more tangible and to give some results, the FOI-VIT starts with taking in just the regions that the doctor looks at. So they're shown here in context. So you can see just the patches that are fixated by the doctor, and we raster stack them. So we completely lose the spatial relationship, but we simply show the patches in the order in which the doctor fixated. And then we pass that through a vanilla vision transformer, and that results in our FOI-VIT. And what's exciting is, as you might expect, this results in a tremendous reduction in the number of trainable parameters, since we're only relying on a fraction of the image, the fraction that the doctor finds relevant for making a decision. But perhaps what's most exciting is that by incorporating this expert gaze, we actually see an improvement in the model performance. So it actually performs better based on F1 score, one of the metrics used to evaluate these models, compared to a vision transformer which does not use gaze. And most importantly, we deliver on our promise of interpretability, because if we now look at the attention rollout of these models, that means the regions that the model actually uses, relies on to make its decision, it's paying attention to regions that we might actually teach a resident to look at, such as the RNFL and RGC probability maps, as opposed to the original vision transformer, which is paying attention to regions that are perhaps less relevant. And for the OGA-VIT, here we're actually modifying the self-attention of the model so that we align with the aggregated eye movement attention of the expert. So what we end up observing here is the model over time actually starts to create a heat map, which starts to look more and more like the aggregated expert heat map, but not purely like the expert heat map alone. Instead, it's an interesting fusion between the model and the expert. So in a way, this is our attempt to try to create something that's hopefully the best of both worlds. And here also, if we look at the final heat map at the later stages of the model training, it's actually paying attention to the B-scan and the RNFL and RGCP probability maps, which are somewhat potentially more relevant regions than either extreme alone. So our effort in developing these kinds of eye movement informed models is to then actually close the loop. And the ways in which we're doing that is using these expert eye movement informed AI to actually guide residents. So with the regions suggested by that OGA-VIT, we then actually highlight those regions on an OCT report and provide them as guidance cues to residents, and see if that improves or impacts their glaucoma detection accuracy, efficiency, and time to diagnosis. So now I'm going to see if I can actually play this video. The audio is not as critical, but just to show you what the system looks like. So you can see here the doctor is actually toggling the brightness, so he can see the regions that the AI is actually suggesting to look at, and trying to see if that correlates with the clinical regions of importance. And then in order to conduct this user study, we also ask them their glaucoma versus no glaucoma diagnosis and their confidence of diagnosis. And so this is an ongoing user study we have to see the impact of this AI on the performance and the improvement, hopefully, of ophthalmic education. So with that, then let me transition to the other story I wanted to tell, which was about portability. So here, of course, the motivation is that even in the US, a large fraction of the population who most needs ophthalmic exams often isn't able to meet that recommendation. And part of the reason for that is the high cost of OCT systems and the lack of access to these systems. So to truly make screening accessible, it's a very compelling use case for AI, but then AI should be able to work on data collected from low-cost portable OCT systems. So that's the motivation for our work. And we started by actually collaborating with a team that has been able to transform these bulky benchtop OCT systems, can have a price tag of 50K or more, to a handheld portable form factor with a 5-fold less cost. And so we actually obtained some images from this portable OCT, as well as the point spread function of this portable OCT. And then we turned to the power of generative AI, specifically generative adversarial networks, or GANs, which rely on the power of 2 neural networks competing against each other. One is the generator, which takes in random noise and iteratively tries to improve it, and the discriminator, which tries to judge whether the generated image is true or not. So over a sufficient number of iterations, the generated image ultimately becomes so good that the discriminator can't even tell between a true image and a generated image. So if we take that a step further, instead of just a vanilla GAN, we can create something called a conditional GAN, where instead of starting with noise, we can actually start with our low-cost OCT and transform it to the quality of our high-cost OCT. So that's exactly what we did. We trained enhanced super resolution GAN to learn the mapping between simulated low-cost OCT using the point spread function of the portable OCT from our collaborators, and training a generator to transform that into the high resolution commercial OCT, which we did have at Columbia. And then with this generator, during test time, we were able to super resolve portable OCT images, and note that they were never used during training. So these portable OCT at test time for super resolution, so we could super resolve them and then apply downstream AI models to actually detect disease. And what we found, interestingly, is that qualitatively, this super resolution process was able to enhance the image. So you can see that the output created by the super resolution model is almost comparable to the ground truth. And you can see that in the portable OCT data as well, which is shown in the bottom row here in the blue and red boxes. If it's hard to see qualitatively, you can see in this image histogram that indeed the output, which has been super resolved by our GAN, has a substantially more frequency across the pixel range. And perhaps most interestingly is if we look at the downstream AI model performance, in contrast to an AUC of just around chance, so 0.5, prior to super resolution. After the super resolution process, it actually increases to an AUC of 0.9, almost 0.9, which actually supersedes the performance on the original commercial data. So this suggests that our process of using these generative models to super resolve indeed allows us to learn the mapping between the low-cost OCT and the high-cost OCT, which is the space on which our AMD model was trained. So we can, even if we don't have access to that high-quality data in test time, or to the experts who can provide this kind of screening, which can be often the case in resource-diverse settings, if we can have instead a system, an OCT system with both AI, super resolution plus AI embedded into the low-cost OCT system, then we have the potential to provide imaging plus AI to much broader populations who need it most. So with those two stories of interpretability and portability, I just want to thank my lab, the AI for VS lab, on our collaborators and funding sources, and happy to take any questions or discussion might have. So.
Thanks, Dr. Kaveri. So I think it's a beautiful talk and really great work. Congratulations to your team. Just wanted to know that, see, both these OCTs were spectral domain OCTs, if I'm correct. Could you
Yes, that's
also go in, see, you are looking at in the resolution of depth, are you able to go? Can you get a more depth resolution by doing this GAN work? Can you increase the depth of the, because that would be an interesting thing that you can probably get the information of a swept source OCT.
that's a really good question. So actually, we are kind of moving in that direction. This work that I showed you was purely using 2D B scans. So we just had I think one 2D B scan per patient. So we wouldn't have sufficient information, I think, to train a GAN to do that enhanced depth resolution. But in a new project that we're working on now, we're actually working with OCT volumes. So we have per patient the full, I think, 128 slices. So it's like, yeah, all the full B scan. So almost the volume, basically the C scan, you might say. And so I think in that case, actually, that is the direction we're moving in. We could do full image to image, not just image to image, but volume to volume translation, and then enhance the quality from perhaps a low cost volume to a high cost volume, and then it basically probe any slice in that generated volume. So that definitely is a potential next step, which we're working on.
Yeah. Thank you. I think one more thing, just wanted to add to the ophthalmologists who are not aware. So we discussed two concepts here. One is a deep learning concept, which was the initial part of the study. It doesn't mean that you only look at images or identify features from image, but even from the gaze. That was the first part. And the second part was another concept called as generative AI. So generating images, new images, which could potentially be a better image than a commercially available device. Dr. Namrata, you want to ask something?
I just wanted to ask how it is going to affect, because the companies do make high-end devices and then some make not so high-end devices. And so if artificial intelligence starts to enhance those images which are from not so high-end devices, how do you think, is it going to affect the economics of or the dynamics of the company who do the high-end devices? Or we are looking more in terms of using the not so high-end devices for screening where, we can take them where these can't go? Maybe Rajiv, you can answer this.
Yeah.
I mean,
No,
I hope you understood what I'm saying.
Yeah, I understood. But I think what you're telling is absolutely correct. I'm not sure Dr. Kaveri can tell that, can it really replace a high-end OCT?
Yeah.
No, I definitely, I think I see this more as a complement, because we definitely need the high, in fact, ideally we need paired data. So data from the same patient taken with the low cost and the high cost. And that's actually work that's ongoing in our lab. What I showed you just now was simulated paired data, where we just had the point spread function of the low cost device, and we simulated the low cost during training. But ideal case, we need the high cost, we need the low cost to train the model. But then during test time, the idea would be to take it in a setting where we don't have access to the high cost. So we would still definitely need our high cost commercial providers, manufacturers, to be like a essential teammate in this process, but hopefully to make their technology accessible in places where like it's like cost prohibitive. So yeah, definitely a team effort.
Thanks. I think we'll go to the next talk, and the next talk is by Rehana Khan. She's a doctoral student at UNSW Australia, Sydney. Again, I'm really fortunate to be her co-guide, and she has worked with me for nearly the last 7-8 years. She moved from Chennai to UNSW, optometrist by profession, who learned machine learning, started working on the models. And one of the similar applications she's also working on, trying to see if we can generate the peripheral image from a central image. Do we really need optos? So that is one of the part of her thesis. And she'll be talking to us on one of the applications of using deep learning. Rehana, you want me to put the slide? Let me try.
Or I can present as well, so not a problem.
Okay, you can
I
present.
can present. Yes. Can you see my slides, sir?
Yeah, can make it full screen.
Yeah, it is full screen now.
Yeah.
Yeah. Thank you very much for giving me this opportunity, Dr. Rajbrahman sir and Dr. Namrata Sharma. So our previous presenter were discussing on the application of machine learning using ocular images as well as some of the OCT and the retinal fundus images. I'll be expanding on how AI goes beyond that and its broader potential. Just a quick note, although I come from an optometry background, I'm now exploring AI. It's a bit like juggling with different size ball, but I'm keeping them all in the air. So yeah, if you ask me, are the eyes truly a window to our soul? I would say no. The eyes are not only a window to our soul, but a doorway to a world of boundless possibilities. Retina, being the light-sensitive layer of the eye, is probably the only human tissue that allows a direct, non-invasive visualization of the microvascular circulation and the neural tissue. And there are a greater number of associations and markers being identified between the eye and the other body system. Keeping this in mind, when we did a literature review, a lot of AI models were developed for the prediction of ocular diseases. And also, studies highlight the retina's potential in identifying the systemic disease biomarkers. Despite advancements in AI, models are still needed for predicting both less explored and more prevalent conditions. And also, the real-world implementations of these models were missing because of its black box nature. Here is our publication on that. Today, I'll describe our anemia prediction model developed using the fundus images. We know that anemia is widespread, with hemoglobin concentration being the most reliable indicator, traditionally measured through invasive blood samples. These procedures are painful, pose infection risk, and produce biohazardous waste. Whether on non-invasive HP estimation methods, their robustness and real-world effectiveness are still under evaluation. Researchers have shown that severe anemia can sometimes reveal specific signs in the retinal fundus, though not all anemic patients exhibit these features, limiting their use as a standalone diagnostic tool. To address this, we developed a deep learning model that uses a retinal fundus images to detect the presence or the absence of anemia. Here, actually, we developed our anemia prediction model using these three convolution neural network architectures, such as VGG16, ResNet50, and Inception V3, which are widely used in deep learning applications. The CNN architecture will be covered in detail shortly, but for now, let me provide a brief overview. The process begins with the input layer, where the fundus images are introduced into the network. Next, the images moves to the convolutional layer, which acts as a feature finder. So this layer scans the image, identifying a specific patterns of features like the edges or textures, similar to how our eye perceives shapes or textures in things we see. Following this, the max pooling layer, it simplifies the information by retaining only the largest value from the data it receives, making the subsequent processing more manageable. The data then proceeds to the dense layer, the decision-making heart of the model, where it integrates all the simplified data to make a determination, like concluding whether an image indicates anemia or not. Finally, the output layer, it delivers the final predictions based on the processed information. Here is a brief demonstration of a model in action. We trained the model using Python programming, which involved executing a substantial amount of codes. So in this clip, I'm showing how the model performance predictions. First, I'll select an image. I'm selecting the first image. It's a bit of time. So yeah, here the model identify as normal. Following that, I'm going to select another image. Where the model predicts anemia. So this will showcase how a model distinguishes between normal and anemic conditions. But
That is not enough. To evaluate the accuracy of a model, we'll generate a performance metrics. Specifically, we use a confusion matrix to provide insights into the model's performance. The confusion matrix will give us valuable information such as true positives, true negatives, false positives, false negatives, allowing us to access the model's precision, recall, and overall accuracy. So in our model, the Inception B3 model achieved an AUC of like 0.98 for anemia detection with 98% accuracy, 99% sensitivity, and 97% of specificity. Though both VGG and RESTED model also demonstrated good accuracy, but the Inception B3 is the winner. Finally, to analyze the area of focus in the fundus images, we generated the saliency maps using the GradCam. GradCam, or gradiented weighted classes activation mapping, is a technique that highlights the region of image that contributes most to the model's performance. So in our anemia prediction model, the saliency maps reveal that the feature associated with anemia were concentrated around the spatial characteristics of the optic disc. This finding is like significant because we have identified a novel sign within the eye that shows greater sensitivity for detecting anemia. We are currently refining this model to identify specific biomarkers for anemia. I might be able to provide more details on this in future. And that's it for now. Thank you very much.
Thank you, Rehana. So I think we understood what 2-3 examples of deep learning, generative AI. This is yet another example where image can be used to detect or predict something which as humans we cannot do. So we cannot tell whether patient has anemia unless they have anemic retinopathy. We cannot see a retinal image and tell whether presence of anemia is there. And we have here power of deep learning, which can now tell us whether the image is anemic of an anemic per subject or not. Dr. Namrata, you'd like to ask anything?
I think Rehana did a very good job.
That's right.
Well explained.
I think we'll go to the next session of our webinar. So we have covered the basic terminologies. We went with machine learning. We went with the second one, that is deep learning. And now we go to convolutional neural networks. And I have real pleasure of inviting Professor Harish Guruprasad from IIT Madras. He's an assistant professor in the Department of Computer Science and Engineering in IIT Madras. And he has been mainly research interest lies in the intersection of statistics, learning theory, and convex analysis. Professor Harish, please.
Hello, can you hear me?
Yeah, we can hear you. You can share your slides.
Sure. Hello, can you see the screen?
Yeah, we can see your screen. You can make it full screen.
Yeah. Can you see it? Can you still see it?
Yes.
Oh, okay, great. Thank you and good morning, everyone. Great pleasure to be here. This brief talk to introduce you all to convolutional neural networks. So this is something which you've already probably seen in this session itself, because there were a couple of models, including VITs, including tools like GradCam, which use CNNs already. Right? But at its core, what is a CNN model? Right? What is a CNN model? At its core, the CNN model is a type of mathematical function. Right? It takes an image as input and outputs a vector of class probabilities. Right? So that's at its core, it's just that. Right. So can you see the full screen?
Yes, we can see it.
Sure. Right. So at its core, it's just that. Right? But how does it do it? Right? For example, in this case, this is an example of a famous CNN architecture, which is about 10 years old, which is called the VGG, Visual Geometry Group from Oxford. So that's it's one of the famous architectures. What does it do? Right? So it takes in an image. In this case, the image is a RGB image, which is 256 cross 256 cross 3, and outputs one of 1,000 numbers, which indicates what is the probability, 1,000 numbers which are class probabilities, right? So in this case, it would say, what is the probability that this is a cat? What's the probability that this is a dog? What's the probability that this is a chair? What's the probability that this is a horse? right? So there are 1,000 such classes, and it takes in an image and outputs these 1,000 numbers, right? So it has more details, but at its core, it's a CNN model is just this. Right? And what are some relevant terms that you will see here? Right? So here are some architecture details, right? So how does it do this, right? How does a CNN model convert this image into these 1,000 numbers? So there are several terms. Some of the common terms that you might see are layers, channels, and neurons, and so on, right? So here is, with an example, I'll tell you what this means, right? So here we can view each of these sheets or each of these cuboids, small, thin cuboids, as layers, right? So that's the example here. So in this particular example, we can see a first 2 layers all have a shape of 224 cross 224 cross 64, right? So the 64 essentially says that this layer has 64 channels, right? The first layer has 64 channels. The second layer also has 64 channels, but I'm just giving an example here. The first layer has 64 channels. And the 224 cross 224 essentially says that each of these channels have 224 neurons, right? So the layer as a whole has 224 into 224 into 64 neurons. So some of these terms like channels, layers, neurons, filters also have analogous terms in the human brain. So it is quite possible that they are motivated by these terms, but they might not exactly correspond one-to-one. Right? Okay, fine. So how do you define these? How are these channels derived from? Each channel is really derived from the previous layer by a convolution operation, right? So that's how each channel is derived, right? So I'll give more details, but at this level, I think the terms to be aware of are channels, layers, and neurons, right? And the model itself is defined by what are called filter parameters or kernel parameters. Okay. So here is I found a pretty decent interactive tutorial for doing that. I'll shift to that, right? So let's see if you can use this. Right. So can you see the screen now? So I've loaded up interactive by right. So here is a simpler model. The VGG net is a more complex model. Here's a simpler model which takes in 64 by 64 by 3, right? So you can see the shape of the image here. 64 by 64 by 3. Why 3? 3 corresponds to the 3 channels, red, green, and blue, right? So that's the 3 channels most images have. And that's the 64 by 64. That's the shape of the image, right? So it takes in that image and outputs one of 10 classes, right? So these classes are lifeboat, ladybug, pizza, bell pepper, ... and sports car, right? So this particular model has been trained reasonably well. So for this particular image, can you see this image, or is this image too small to see?
We can see it. It's okay.
You can see. Okay, right. So this image is a sports car, and this particular model is correctly saying that this is classified as a sports car. Right? So using our terminology, this particular model has, well, I'm going to say just 4 layers because the grouping indicates this, right? So this corresponds to layer 1, this corresponds to layer 2, this corresponds to layer 3, and this corresponds to layer 4, right? So here you have 62 by 62 by 10, right? So this particular layer has 10 channels with 62 by 62 neurons each, right? Okay, so how are these? I said that each channel is derived from the previous layer, right? So this is called an input layer, right? So this is the input layer, which is really just the 62 by 64 by 64 by 3 image. The image itself forms what's called the input layer, right? How is, for example, this particular channel derived from the previous layer? For the first layer, the previous layer is just the input, right? So how is this particular, here is an illustration here. How does it do that? It does this by the operation called convolution, right? So this, the operation convolution gives the name convolution neural network, right? So what is convolution? I'll tell in a little bit more detail soon. But this convolution operation is defined by a kernel filter, which converts the previous layer into this particular channel. Right? And similarly, there are 10 channels in this layer. Each channel is defined by a different filter or kernel parameter. And this happens for the first layer. And similarly, the second layer is just derived from the first layer, right? So the first layer is derived from the 0th layer. 0th layer is just the input. And the second layer is derived from the previous layer, which is the first layer, right? So there are nonlinear. So these mappings that transform the previous layer to a channel are actually linear in nature, right? So it's effectively equivalent to just weighted additions, weighted multiplications and additions. But then you also have a nonlinear activation, which is common for pretty much all deep models where you have a nonlinear activation. In this case, it's what's called a ReLU activation. The details are not that important. So you have layer 1 and which operates on the input, layer 2 which operates on layer 1, right? So layer 2 also contains 10 channels. Each channel is derived from the previous layer, which contains 10 channels itself, right? So that's how most of deep network architectures work. They operate in layers, right? So the ith layer depends only on the I-1th layer. There are exceptions, but that's the broad theme that you will find in. That's why it's called deep, right? So which is you can build layers on top of each other. So it's easy to build models which have, let's say, 100 layers, right? So that's why it's called a deep network, right? So it's each layer builds on top of the previous layer, right? So that's a very brief overview of the CNN architecture. The details are not that important. This level of detail is reasonably sufficient for our purpose, right? And yeah, so you do all these computations, and towards the end, you convert that into 10 numbers, which essentially express what is the probability that this particular image is one of the 10 classes, right? So that's the CNN architecture briefly. Right. So I'll come back to my slides now. Can you see the slides?
Yes. Yes.
Oh, great. So I talked about the convolution operation. What is the convolution operation, right? So here is an example illustrating how the convolution operation actually works, right? So this blue image can be correspond to, let's say, layer I, and this filter, which is, or the kernel, which is the green matrix that transforms the blue input into the output. How does it do that? It does it through what's called the convolution operation. But what is the convolution operation? So the green is the output and the blue is the input. And this gray patch that seems to be moving, that corresponds to the filter or the kernel, right? So that's in this case, this filter is given by a 3x3 matrix that moves around the input image, right? And when it, for this particular pattern, let's say it just does an element-wise multiplication and then addition, right? That's element-wise multiplication and addition, shift. Element-wise multiplication, addition, shift. That's what's happening here, right? So here you have a 5x5 input, which gives a 3x3 output. And each element of this 3x3 output is essentially a result of an element-wise multiplication of the filter with the previous layer and addition. That's why these are linear operations, because the only thing that's happening is multiplication and addition, right? So it's element-wise multiplication and addition, so it's a linear operation. So this has a name which is called the convolution operation, right? So right, that's sufficient for our purpose. Okay. All right. Right. So with that, so what do channels represent, right? So okay, that's fine. That's the architecture and it works well. But you can ask the question, okay, what do channels represent, right? So the current understanding, this is still an open question. There is no clear answer to these questions, but at least the current understanding is that each channel in a layer corresponds to an input pattern detector, right? And each neuron in the channel corresponds to detecting the pattern in a particular location, right? For example, here is a particular deep network with the channels visualized at different layers, right? So the early layer channels correspond to detecting simple pattern like textures. And as you go deeper, like the later layers detect more and more complicated patterns, right? So this here is I've grouped channels according to layers here, right? So the further right you go, the deeper in the network that you are going. So the current understanding is that early layers detect simple patterns in the input images, and later layers, you can see, for example, a layer that is close to the right end is actually detecting quite complex patterns. In fact, it seems to be detecting things like football shots. It seems to be detecting things like eyes. It seems to be detecting things like dog ears and so on, right? So each channel in a later layer, for example, in the example that we saw here, let's say in this case, and a channel in, let's say, in a Con5 layer would correspond to quite complex patterns in the input image. A channel in, let's say, Con1 layer would correspond to reasonably simple patterns like this, like the one on the left, like textures or lines, horizontal lines, vertical lines, and so on. Right? So here is an interactive visualization, which I'll not go to due to lack of time, but there are lots of interesting visualizations for CNNs, mainly because CNNs are really designed for images, and images are a very nice very easy to illustrate, right? So with examples. Okay, so how are these CNNs learned or built or trained? Well, the parameters of the model are really the convolutional filters, and the parameters are set to a value that minimizes the discrepancy between the model output and true class labels on the training data, right? All supervised models are trained this way, so which we saw earlier in today's session. Most CNNs are trained using supervised techniques. There are unsupervised techniques as well, but they are really mostly just unsupervised models. The final utility or accuracy of the trained CNN model is highly dependent on the quality and quantity of training data, right? So here is an example. To achieve human level accuracy on a classic 1,000 class classification task, CNN models need to be trained on about 1 million pairs of image, class label, right? So that's the order of magnitude of data that is required to achieve human level accuracy. Okay, so then question, why CNNs, right? So CNNs, yes, that's an architecture, it seems to work well, but why do they work well for images? CNNs are state-of-the-art models for most image-based tasks because of properties of image-based data, right? And similar properties of the convolution operation, right? So what are those properties? The main property is translation invariance, right? So for example, let's say you are classifying a particular image as a cat because let's say there's a cat in the top left corner of the image, right? You can essentially shift the image where the cat moves from the top left to the bottom right. The class of the image does not change. The class of the image still remains cat. The image has changed significantly, right? So the image, if you view it at a pixel level, the image has changed significantly, right? So the cat is moved from the top left to the bottom right. The image has lot of pixels have changed significantly, but the class of the image has not changed, right? So why is that? Because a lot of images have some level of translation invariance. So if parts of the image move, the output is the desired output does not change, right? So that is the image data have this property, and convolution also has this property, because you can see that the core convolution operation is element-wise multiply, add, and shift, right? So this gray thing, which corresponds to the filter, is the same, right? So all neurons in the same channel are essentially detecting the same pattern in different locations of the input. So that's that really corresponds to your CNN having translation invariance, right? So that is, it doesn't matter whether the cat is in the top left or the bottom right, it will be detected by that particular channel corresponding to detecting cats, right? So that's so because of this alignment between what we desire in the model, which is some form of translation invariance and rotation invariance and scale invariance, and what properties that the convolution operation provide, there's a natural match, and that's the reason why CNNs are really state-of-the-art models for most image-based tasks, right? So there are these newer models like vision transformers, VITs, which are also state-of-the-art, but they also use a significant bit of convolution themselves, right? So there is convolution is inbuilt in pretty much all state-of-the-art input, state-of-the-art image tasks. So I just mentioned that CNNs are things that transform images into class probability vectors, but there are lots of CNN-based models which do far more sophisticated things. So here's an example of what's called as object detection, localization, and classification, right? The classifying an image as one of 1,000 classes is nice, but that's not a realistic images, right? So that question need not even make sense, right? So if I gave you this image and I asked you to classify this image as one of 1,000 classes, which involved people, cars, roads, you can't really say the answer because all of them are here, right? So this particular image contains people, cars, roads, traffic lights, all of that is here, right? So image classification makes sense only for well-curated images which have only one class in them, right? For most realistic images, like for example, surveillance videos and so on, that's not a realistic expectation, right? So you can't expect that a typical image that a surveillance camera sees is going to have one nice cat centered in the middle of the image. That's not a reasonable expectation. This is more of a reasonable input that you can expect. And for these kind of things, what you really need is to detect the objects find out where the images are and classify those objects, right? So here example, you can see that there are lots of bounding boxes over different objects. So you can see there are several car boxes, there are several people boxes, there are several traffic light boxes, and so on, right? So you can easily imagine how something like this would be useful for, let's say, if you are building an automated car, or let's say you are building an app which does this, and for, let's say, some visually impaired person, and you can put this on a, let's say, a glass, on a cooling glass or a sunglass, and this glass would essentially convert it into audio and say that there are 5 cars and 7 people on the street in front of you, right? That's something which a visually impaired person can really use. Right? This is already possible, right? So this is already possible now, where there are models which can take an image and output something like this, right? And of course, you still have to translate this into something that a visually impaired person can see, can actually understand. So you might use something on top of this, like something which will translate this into an audio feed or something like that. Or you can imagine something like this being useful for surveillance footage, where you quickly have to track how many cars are going. Or let's say you're building a traffic camera, which is supposed to detect speeding cars, right? These kind of tools are, again, very useful for that. And another task that's quite often used is image captioning, where you give an image and you don't classify the image, but rather use natural language to caption that image, right? So here is an example image, and the model says a woman is throwing a frisbee in a park. And here is an on the right is another example image, and it says a dog is standing on a hardwood floor, right? So now it's not classifying one of 1,000 classes, but rather it is using natural language itself and generating captions. This could potentially be more powerful, but again, there is no way to correctly, you can't do accuracy, right? So if it's just 1,000 classes, you can count, okay, there were 100 cats in my data set, and my model said that out of the 100 cats, only 75 of them were cats. So my model has 75% accuracy. You can say that, but here accuracy becomes hard to verify, because how would you say this caption is right or wrong? What if the caption is mostly right, but it is wrong somewhat, right? For example, here it says a dog is standing on a hardwood floor. The model seems to have discovered that there is a dog, but there is no standing, right? So the dog is clearly not standing. So it is wrong, but how wrong is it, right? So the accuracy and those kind of metrics become hard, but these are more applicable in the wild, right? So which is something like this could actually automatically be useful for a visually impaired person. There is a model which takes in the image and summarizes that as a text or as an audio thing, right? So that's if it is reasonably accurate, it doesn't need to be 100% accurate, but if it's even reasonably accurate, that can help the person understand what's going on around him or her. So that's a brief overview of CNN architecture and CNN-based models. I'm happy to take any questions.
Thank you, Dr. Harish. We will go to the questions after the next talk, which is again related to CNN example. And I would like to invite Dr. Raghu Prasad. He's a prominent researcher at Zeiss, and he's been focusing on mainly ophthalmic technologies and enhancing the clinical workflows by integrating AI and deep learning into them. I have worked closely with Raghu, and I think he's one of the very good scientists who has both the domain knowledge of ophthalmology and of AI. He's a PhD, and he has done a significant work as far as AI in ophthalmology is concerned. Raghu, please.
Thank you, Dr. Rajiv. Thanks for giving me this opportunity to present the work that we had done very recently. So I'll share my screen and get started with the presentation. So is my screen visible?
Yes.
Yes.
Okay. Thank you. Thanks for inviting me for this session. Basically, I'm the head of advanced development at Carl Zeiss Research India. So we have been collaborating with Shankar Netralaya and Dr. Rajiv for a long time, and he is one of our strategic partners to give us certain problem definition and foster innovation in the field of retina and related research themes. So we started this collaboration with Dr. Rajiv a few years ago, and now this has been nurtured into a full-fledged tool. So I will get started with the basics and the fundamentals and the motivation behind this retinal example that we have taken for this presentation. So basically, I'm going to now describe about this example known as diabetic macular edema or DME response prediction. So the major motivation behind choosing this example was to understand how effectively CNNs or the neural networks help us in predicting the response to the anti-VEGF injection from the patient. So this is one of the key areas of research which needed certain initiatives from both the clinical point of view and also the research and the technical point of view to understand how best we could join hands with experts like Dr. Rajiv to understand the major use cases in the field of retina and develop an AI model which will help patients in the moments that matter. So this is one of the key initiatives between Shankar Netralaya and Zeiss, where we have developed a prediction model which takes the OCT data. So you can see here on the screen, like we have the B-scan volumes of OCT data sets that are acquired from the Cirrus OCT scanner of Zeiss. And then it takes into account other clinical parameters of the patients, like the visual acuity, the near BCVA, the far BCVA, the anti-VEGF injection count, which has been administered in the past, and a few other parameters like the patient's history, the duration of any illness such as blood pressure, diabetes, and so on, and what is the surgical history of the patient, like whether he has undergone any surgery in the past, and so on. And it tries to model the response without using any invasive parameters. So the main intention about going ahead with this research theme is to utilize technologies such as convolutional neural networks and different classification networks that are here at our disposal to use some of the key technologies to grasp certain characteristic patterns which are available in the images. So the idea here is to ensure that the cognitive stress and workload on the ophthalmologist is reduced to a larger extent by creating an AI-based assistive technology toolset that takes as an input certain images. It could be OCT, it could be fundus photographs, it could be other angiographic images like the swept source OCTA and so on. And then it could also include certain clinical parameters, which could be numerical, which could be even statistical parameters, and then model the difference of the characteristic patterns that are assessed in the image, and then come out with a suggestion on whether this patient is going to respond to the futuristic injections or not. So because when the patient is administered the anti-VEGF, it's an invasive procedure, and it also has certain amount of implications on the patient's health, because multiple anti-VEGF injections that is registered to understand whether the patient will clearly respond to the DME based symptom is something that has going on for a long time. But no study has concluded on what sort of role AI will play in understanding the implications of constructing a classification model to classify the patients and whether it is going to respond to the anti-VEGF therapy. So similar such attempt has been made here to investigate how best we could evaluate the responsiveness of the patient in identifying whether the patient is going to respond to future injections, or should we be administered a steroid for futuristic line of treatment. So this is one of the baseline that we have observed here, because we have collected many samples. So in the clinical setting, we have recruited certain patients, understood their clinical parameters, collected both retrospective and prospective data, which consists of the OCT scans and the other clinical parameters which are outlined here. And this clinical parameter was used to like process the data set and then feed the processed data to a CNN model. So in the subsequent slides, I will cover those details. So the idea here is to understand how best we could compare the characteristics that are observed in the Indian population versus other global populations. So for that purpose, what we did is we collected huge data sets, around 900 plus patients data, understood their underlying disease patterns, modeled those disease patterns in terms of a patient specific model, which would identify the behavioral characteristics of the patient, the past lifestyle, the sedentary lifestyle history, what sort of family history the patient has, and has this disease been progressing over a period of time, and what sort of implications this disease has on the day-to-day lifestyle of patients. So such things were recorded and modeled from the data that was available with the patient history and so on. And then we also identified the central subfield thickness and the CST volumes, like for example, what sort of fluid pockets that were identified in the image, like the intraretinal fluid, there's a subretinal fluid, the PEDs, and we computed the volumes of each of these parameters. And these were also used to determine whether the patient is going to respond for the anti-VEGF therapy. So in addition to the OCT image, we also understood that there is a huge amount of clinical parameters. It could be a numerical parameter, it could be a non-numerical parameter. We were also interested to model this using certain support vector-based regression models or the non-deep learning models. So here is one such example where we didn't use any deep learning models, but we tried to use certain machine learning models to identify whether there is a strong correlation that exists between the parameters that are captured for the patient and whether he's going to respond for the anti-VEGF injection or not. So we use several techniques such as radial basis function, the linear classifier, the polynomial classifier, random forest, and so on, which are different machine learning techniques to identify whether there is a strong correlation between the clinical parameters and the anti-VEGF response. So unfortunately, we found that with clinical parameters alone, there could not be any special relation that could be derived out of these techniques, and there was no strong findings to suggest that the clinical parameters alone is responsible for driving the classification response of the patient towards the anti-VEGF therapy. So that's where we were motivated to understand how best we could include image parameters and also different image selection models to this specific clinical parameters. So that's where we captured the OCT images with the 12 central B scans. So the B scan volumes were assessed, processed, and then the outcomes of the analysis of the B scan volumes were combined with this clinical parameters to identify the classification category on whether the patient is going to respond or not. So this slide gives a holistic overview of the CNN architecture that was used to build a multi-model classifier. So the multi-model classifier is nothing but a combination of two different data sets here. So the two different data sets are nothing but the OCT B-scan volumes data, which is known as a OCT cube, which contains around 2048 odd features, and then the structured data, which is something that is acquired from the hospital electronic medical record. So the idea here is to combine the structured data information with the image characteristic information. So from the image point of view, the images were 512 by 512 B-scan volumes of the patient, where the patient has undergone multiple visits of diagnosis, and then the anti-VEGF injection administered after the scan was taken. And there were some images where the scan was taken before the anti-VEGF was administered. So we wanted to understand what sort of pattern changes that occur in images before and after the anti-VEGF was administered. So we wanted to extract those features and identify the feature vectors, so which are nothing but the important characteristics that will help us determine what is the classification criteria for segregating the patient into responsive and non-responsive category. So that's where we used significant amount of data set, and then like use the images which contained 512 by 512 and 1024 by 512 with 128 central B scans, and then modeled that with certain parameters like identifying the sharpness of the image, then identifying the Gabor transformation of the image. Then we used something known as SC-ResNet, which is a classifier, and this classifier is a well-known classifier in the neural network domain, where it can identify the features that are embedded in the image and use these features to output the class labels or the class probabilities. So typically, as the previous speaker spoke about the convolutional neural network architecture, it contains an input layer, a hidden layer, and an output layer. So I've just tried to illustrate what sort of different layers were there in our architecture. So it consists of a dense layer, regularization layer, a softmax layer, and then a class probability layer, and so on. So basically, the class probability score is something that happens once the softmax layer provides the decision on which class this feature vector belongs to. And this CNN was something trained with multiple parameters of data sets, like varying parameters, and also there were certain complements of data that were generated. We generated synthetic data also in addition to the original realistic data that were created, just to make sure that the CNN is capable of passing through all corner conditions and all corner cases. So by this, we were now successful in identifying how effectively, given an OCT image of the patient and given the clinical parameter of the patient, how best the CNNs could classify this patient to a non-responder or responder without the anti-VEGF being administered. So let's say you administer the anti-VEGF injection with the count of 5. So that means 5 injections has already been administered. And before administering the 6th injection, you want to run this model and first try to get a baseline recommendation from the model on whether the patient is going to respond or not. So if the output of the model says he's going to respond based on the previous data of the 5 injections that has been fed to this model, so you go ahead and then administer the anti-VEGF injection. And if the model says he is not going to respond, then you can then discuss with the clinical team and understand what is the next line of therapeutic treatment that needs to be given to this patient, whether it can be a steroidal treatment or something else is that needs to be determined. So all in all, this tool is just a recommendation tool, which is going to say that this is the classification label of the responsiveness detection. And based on this, what sort of decisions you need to take further is purely up to the discretion of the clinician. So this was one of the key initiatives that we did with Shankar Netralaya, and now this has matured to a larger extent. So in summary, we were able to develop the diabetic macular edema model with certain parameters that were assessed here is the central subfield thickness, the age of the patient, the diabetic retinopathy stage, whether he's in a proliferative DR stage, a non-proliferative DR, mild or severe, and so on. Then what is the pre-OCT central subfield thickness volume, because this is one of the key parameters that was found to influence the anti-VEGF response condition from the AI model. And then certain other parameters like the average volume, the count of injection, how many times the injection has been administered, and of course the visual acuity from the Snellen's chart or something like that was used here to identify the visual acuity parameters. So basically, we classified the patient into a responder, which means that his CST volume has increased, decreased, or remained the same to 10% of the pre-treatment CST volume. And a responder is something like the post-treatment CST is reduced by more than 10% compared to the non-responder, which was less than 10%. So these were the two definitions of responder and non-responder. So, and here you can see the accuracy scores. We found that the multimodal classifier had better F1 score compared to the other approaches like the cube data or the image classifier alone and the clinical parameter classifier alone. So to our investigation, we found that combining both image data and the clinical parameters yielded in better F1 score and close sensitivity and specificity compared to the other methods. So that's where we wanted to pursue the multimodal classifier now, and there are multiple experiments that are going on to fine tune this and make it more viable and accessible solution to the clinical customers. So this is a small demo now. I'm going to show a small demo of how this worked, and thanks to Dr. Rajiv for facilitating this tool evaluation, because this was one of the key things that we wanted to showcase as a part of our collaboration with Shankar Nethralaya, which opened the gateway for new research themes and also the new collaboration initiatives that we plan to have with the SN team. So this is a tool which contains multiple apps that are hosted on the health data platform. So Zeiss has something known as a HDP platform, which is a suite of clinical applications. And you can see here, you can select the DICOM file of the OCT cube. So the DICOM files are nothing but the raw files that are obtained from the OCT scanners. And you can select them from your electronic medical record or the Cirrus scanner itself. And then you can key in all the parameters here. So right now you are typing all these parameters manually, but in future this parameters will be pulled from the electronic medical record. So the manual effort will be very less, and you need not spend additional time in populating these parameters. So now once all the parameters are selected, like the DR stage, the visual acuity, injection count, the pre-treatment CST, and so on, the algorithm will process the information, and then it will assign the patient IDs and the patient name, and when the processing was happened. And then you can see that there is processing going on in the background where the AI model will get invoked, and the CNN architecture will be fired up, and the CNN will do the processing of the data and also the clinical parameters along with the image, and give us an output. So on the right hand side, you can see the response from the algorithm. So it says, like, based on the evaluation of the variations of CST, the patient is categorized as a non-responder to anti-VEGF injection. So this is again just a assistive technology, a cue to the clinicians to understand what type of treatment they need to plan, but how best they could accept this recommendation from the AI model, and then plan the therapeutic treatment for the patient is up to the clinician's discretion. So you can scroll now to all the B scan. So B scan is basically a volume. It contains many images. So for each image, what is the responsive decision from the algorithm is something shown on the right hand side screen. So this is one of the tools that we would like to collaborate further with Shankar Nethralaya and make it more accurate and precise, so that the medical community can get benefit from this collaborated tool set and the approach that we have taken here. So thank you, Dr. Rajiv and team, for helping us develop this tool. So with this, I end my presentation and will be glad to accept any questions from the team.
Thanks, Raghu. I think the aim of this session was to understand CNNs and how it has been used, and extensively he has used it. Now, being a clinician, I'll go to the other side. When we saw this and it works pretty well, but we know how we determine a non-responder. We look into inflammatory response. We look into OCT biomarkers. And that was a work which I did with Professor Sundaresh and Raman. So a very unique approach we tried. We looked into inflammatory uveitic macular edema and tried looking at all the OCT biomarkers in uveitic macular edema, quantified them, and tried using that in diabetic macular edema. And I am very happy that that also worked pretty well. That means the way we look into a disease to identify a responder, non-responder seems to be correct. And that was actually one of the best PhD thesis of one of my, not PhD, sorry, DNB thesis of one of my student. So these are the type of applications we can think of when we use machine learning. I think we are a little bit running off the time. We'll keep the questions till the last. And I would now request that we go to the next theme of transfer learning. And I request Professor Zhang Yin, who is a researcher at Google Health, and he's been focusing on AI and health outcomes. And we'll be, he has a recorded talks. We'll just request, can you just play the talk? Yeah.
Hi everyone, I'm Xiang. I'm a software engineer from Health AI at Google Research. From the last session, you probably have learned about the CNN models. And next, I will talk about transfer learning and fine-tuning, the techniques used to adapt CNN models to different use cases. Quick disclaimer, I am an employee of Google and I own Alphabet stocks. Here is a quick overview. I will first talk about the concepts of transfer learning and fine-tuning and provide an example. This is a fast-growing field and what was used in a few years. Let's take a look at how the ARDA-DR model was created 8 years ago and how foundation models are used today. First, quick recap. This is the CNN model architecture, which has many layers of neurons shaped like a pyramid to process visual inputs into a final output. To make things simpler, let's divide the CNN models into two parts, the embedding model and the classifier. The embedding model, which is the lower part of the pyramid, extracts information from the input image. And the classifier is a few top layers of neurons that generate the final output based on the results from the embedding model. In fact, most of today's CNN models start from a pre-trained model. The pre-trained model was usually trained on a very large dataset like ImageNet. The pre-trained model has learned how to identify basic patterns like edges, so people don't have to retrain from scratch. This is actually called the transfer learning, which is leveraging knowledge acquired by a pre-trained model on large datasets and use smaller datasets for specific tasks. There are two basic types of transfer learning. First one, feature extraction, and second one, fine-tuning. Feature extraction is basically to add a new classifier on the existing embedding model to train the model for a new task. Fine-tuning is to unfreeze the classifier or even the whole model to and use a smaller dataset to improve the overall model performance on certain tasks. Let's take a quick walkthrough on an example. So we start from an untrained CNN model and train them with a large number of images in the non-medical context, for example, the ImageNet, and then we'll get a generic pre-trained network. In step 2, we want to do some domain-specific pre-training. So in this case, we have labeled chest X-ray images to feed into the model and create domain-specific embeddings. In step 3, we will use various transfer learning techniques to further improve this model by either retraining the top layers for better classifications or using a relatively larger dataset to fine-tune more layers or even the full network. So machine learning has advanced dramatically in the last decade. Let's take a look at how we trained ARDA 8 years ago. ARDA is a CE-cleared medical device developed at Google that uses a CNN model to help detect diabetic retinopathy. It has screened over 500,000 patients since 2019, most of whom are from India. To train the ARDA model, we obtained 130K retinal images and have them labeled by 54 ophthalmologists. These data were further split into 3 parts, the train, tune, and test sets, to further train and evaluate the model and get the best performing model for deployment. The CNN architecture of the ARDA model was Inception Wave 3, which was pre-trained using the ImageNet. Nowadays, there are a lot of more and newer CNN architectures that people can pick from. Following the development of ARDA, we also explored ways to adapt the model for broader applications. However, fine-tuning AI models in the healthcare setting presents a unique challenge: the regulatory approvals. It is very likely after you fine-tune a diagnostic model, you will need regulatory reviews and approvals before you can deploy it. And this time can be very time-consuming and expensive. Therefore, it might be worth to consider some alternative strategies to enhance the model performance without directly modifying it. We could use a supplementary non-diagnostic model to explain or catch camera or image quality issues, so operators can take better images for the patients and indirectly improve the outcome. Nowadays, foundation models have emerged as a new approach. These large-scale models are trained on massive amounts of unlabeled data from specific fields, therefore enabling this model to learn domain-specific generalizable representations. This offers a significant advantage. Downstream users can then fine-tune these models with smaller, specific datasets for their unique needs. A notable example in this field in the retinal imaging is called the Retinal Foundation model. And this model was developed by the Pierce team from UK. That's all from me today. Please feel free to reach out for more questions. Thank you.
Thank you. I think, so we were part of the first study, the ARDA study, and we have seen long way after that. Really, the networks, the way the algorithms have been made has changed. And from Google Health, I think you understood what this transfer learning is. I still remember our JAMA paper had one of the things written that to get the accuracy after 60,000 images, the accuracy didn't change. That means you need minimum 60,000 images. But now with transfer learning, even less number of images, even the diseases which are rare, you can still create an AI algorithm for them. I think that is the key message as far as transfer learning is concerned. Foundation models are extremely good, and happy to share that there is a global consortium now creating these type of ophthalmology specific foundation model. The first one was by Dr. Pierce on the RetFound model, but now we have many of these coming up. I think we'll go ahead with the next talk and then at the end have some discussion because time is short. So happy that we have Professor Bin Sheng with us. And Dr. Bin Sheng is a full professor and a PhD supervisor at the Department of Computer Science and Engineering in Shanghai Zhaitong University. And he serves as a deputy director of the Institute of Computer Application and leads the Intelligent Healthcare Initiative in the ministry. I've been collaborating with Professor on a couple of projects, and it's real pleasure having you here. And he will be sharing with us some basic concepts on LLMs. You want us to play the video?
Yeah, I can share the slides. Thank you.
Okay, you can share. Sure.
Yeah, hello everybody, and thank you very much for Professor Rajiv's invitation. And I think this is very international and high level conference, and I'm very I'm honored to be here to share some of our research. So today I will share some of my opinion about the understanding large language model and their role in processing clinical text data. So this topic will relate to my previous research is the DeepDR LLM. So I will, based on my research, I will share some of my thoughts about this direction. For the let's start about the background of the diabetes and the diabetic retinopathy. And as we know, there are a lot of insufficient healthcare resource and the lack of trained the primary care physician of the diabetes care in low and middle income countries. And we also lack of specialized eye care services and cost-effective diabetic retinopathy screening program in low and middle income countries. So this is a big and global public health challenge. And in artificial intelligence and in medicine, I think the diabetic retinopathy is a very special domain because I think one of the first deep learning application or program is made by Google team, and I think all of us know in 2016 the Google published a landmark paper, not just in AI ophthalmology but also in AI medicine. Is proposed deep learning algorithm for detecting DR in JAMA, and this system could achieve very high accuracy for detecting referable DR. So this is, I think, I talked to Professor Tian Huang, and Tian Huang said at that time when he saw this research, he cannot sleep, and he said this is kind of a game changer, and just have a new insight to use a deep learning, such kind of black box AI algorithm can detect the fundus image and can get a very, very high accuracy of the detection, the DR detection. And at that time, it's very, very revolutionary step to see, okay, what is the potential of the deep learning. And after 1 year, and the Singapore National Eye Center published another landmark paper, and to extend this kind of deep learning algorithm for detect not just on the for the diabetic retinopathy, but also for other related eye disease, and also that this system was validated among multi country population and with diabetes. So from Google and from Singapore, and we see the deep learning is very worked very well for the for detection DR system, and this accuracy is also very high. Not just only for the DR, but also for other eye disease. And we actually, our team in China, actually at that time, we learned from these two landmark paper, and we, based on this landmark paper, we further develop a system, a deep DR system, and this system actually can perform a real-time image quality assessment and also segmentation of the retina lesions, and also can give the grading of DR and the DME. So we use this kind of deep learning and to get multiple function or task, and we can get different kind of result cause the from the early and to late stage of the DR, and we can have a very high accuracy, and we have the quality feedback and also the lesion segmentation. So this is somewhat comprehensive system, DR, deep learning system, and to detect the DR. And we also see when we use this kind of, in this system, actually we use the pre-training models. At that time, it's not called foundation model, but we actually, this is kind of pre-trained model. And we use the pre-train, we can get a very high accuracy. And yeah, so we see OLinsen-3 deep learning system for the diabetic retinopathy are based on the deep learning algorithm to detect the DR from the retinal imaging. They were built on the convolutional neural network, and the development with the transformer models, foundation models, and the generative AI in recent years. We see the large language model and the pre-trained model now is become more and more mature and bigger, and they can help us to recognize and understand not just for the lesion and also the grid of DR, but also they can have the have to classify and to generalize the language and according to the content and purpose, and to have us can generate appropriate and coherent response. So it's actually gives some insight for us. I think in the last year, and we actually we used the whole year to think about how to optimize the large language model and also deep learning, image-based deep learning technique together to have a better depth scale or DR scale. So this is what we think about. And we see that at that time we saw the like GPT or Llama, actually they do have some language generation task, can make some like simple management text about related to the DR status or the diabetes stages. So so we think about why we can combine these two parts together. For example, if we have a deep learning algorithm and we can detect the DR grid and the lesion, and we can use this and we transfer this into a POMOD, and then we can input this POMOD into the large language model. Maybe we can have a more accurate, more precise recommendation text. So this is the original source about the DeepDR LLM, and we can use this way. We can combine the generative AI and the foundation model together, and to have a more like the recommendation, not just for the diagnosis, but also for the treatment or management of the diabetical people. So this is the motivation for this algorithm. So we can see that in this slides, we can see that the GPT and the large language models are all actually belong to the foundation model and generative AI. And we can what we can do is to try to use this kind of language function and to combine the image together, and we can get the result. So early in this year, we published a perspective on the large language model for diabetes care in the Science Bulletin, this journal, and we propose that to fine-tune the open source large language model with diabetes knowledge is a potential way to develop the large language model, especially for diabetes care. And following this idea, we actually develop and validate integrated image-based deep learning and language model for primary care, primary diabetes care. So this system is called the DeepDR LLM. Professor Raj actually gave a lot of support for development and validation for this system. And this is actually the first collaborative paper published online in Nature Medicine in this June. And this system actually have two modules. The module one is the large language module. We call the LLM module. So this module provides individualized management recommendation for patients with diabetes. The module two is the DeepDR transformer module. So this module is like a traditional image deep learning module to give the image quality assessment, lesion segmentation, and DR grading from the standard or portable fundus image for each patient. And then we can use this kind of output of module 2, that is deep DR, deep learning module, and to use as the input for the language module, and then we can have a more precise management text to help the doctor to give the recommendations. And first, we use over 0.5 million standard and portable fundus image to train the transformer module and to fine-tuning of this large language module. We use 0.3 million real-world management recommendations. And this kind of fine-tuning of the large language module, actually, we use adapter and a neural technique based on our Chinese diabetes care recommendation data, and we can have fine-tune the Llama module, and we can have a more or better recommendation functions compared with the original Llama model. And since the DeepDR LLM system was successfully developed last year, and our team actually carried out a multi-faceted evaluation of the system for the safety, reliability, controllability, and the fairness. And our team actually invite 10 scholars from the diabetes-related disciplines and to form an international expert committee. And the research team first randomly select 100 cases from the China National Diabetic Complication Study. And then the expert committee form a consensus of the management recommendation for each case. And this kind of consensus is used as the model answer for the following comparative evaluation on the management recommendation given by our assistant and the primary care physicians. And the result shows that the quality of diabetes management recommendation produced by the DeepDR LLM system reached or was better than that of primary care physicians. And also, our system was externally tested using more than 0.5 million fundus images from Chinese cities such as Beijing, Shanghai, Guangzhou, Wuhan, and Hong Kong, and also other 6 countries, including Singapore, India. Of course, this is supported by Dr. Rajiv, and Thailand, and United Kingdom, Algeria, and Uzbekistan. And the diagnosis capability of this system reached the level of professional ophthalmologist. Furthermore, through an independent reader study involving Chinese primary care physician and Singaporean professional graders, the team also proved that the primary care physician could detect DR more accurately with the assistance of the DeepDR LLM by using the fundus images extracted from the representative data sets, including China National Diabetic Complication Study and the SEED cohort study. So look back about this study, we think that so the large language model, at the beginning of the large language model is not considered as a multi-modality artificial intelligence model, but now we see that the LLM become more and more multi-modality. So if we consider this kind of LLM will become as a multimodality foundation model, and if we can use this kind of very new and very powerful AI tool, and we can have a very promising perspective for the AI used in diabetes care, including the personalized health coaching and the food guidance and the blood glucose monitoring, and also other diabetes care management, and also the mental health support. So now our team is working on this way, and we try to make this large language model become more and more foundation and more multimodality. Thank you.
Thank you, Professor Ben. It's been real pleasure working with you, and what you told about the large language models. I think it's important that rather than looking at that as alone, integrating it with the deep learning and coming out with algorithms which can really solve day-to-day problems. Just like to share the Indian results. One simple thing that we also tried tracking what would be the progression. And what we found that we can actually increase the follow-up to nearly 3 years. You need not call them every year for a screening. The average screening interval was nearly 36 months. I think that these are the translations which can happen. And we are aware that it's always better that just getting presence of DR or absence of DR, if we also get a clue that how it has to be managed, the diabetes care comes along with it, it goes a long way. We could even show in the primary care settings, the same findings what they found in China was there in India too. So I think there are a lot of implications of these studies. We will have questions after the last talk. And I would now request Dr. Patrick Zhou Yu. He is an intern physician. He'll give a real physician perspective on how these large language models can be used in real settings. You'd like to present it, or shall we play or talk, whatever you say?
Maybe you can just put the recordings.
Yeah. Viraj, can you put the recording? Would start it.
Okay. The
Can't
audio
hear,
is.
I think we can't hear.
Oh, maybe. Okay. Maybe I just inserted the audio into the PPT file.
Thanks very much for Professor
We can hear now.
for me to deliver this presentation. Today, I am going to share the application of large language models in retinal care data analysis. As Professor Binson just introduced, we have developed an integrated image language system for primary diabetes care. The aim of developing such system is to deliver precise management recommendations for people with diabetes. So what is precision medicine? Precision medicine is contrary to one-size-fits-all treatment regimens. It's more tailored for individuals. It means the right interventions for the right patients and at the right time. Let's look at some examples generated by DeepDR LLM. The first case is a case with severe non-proliferative diabetic retinopathy. DeepDR LLM will recommend this patient to be referred to the ophthalmology department for further examinations urgently and further laser or surgical treatment. The second case is a 79-year-old female with type 2 diabetes. DeepDR LLM will recommend this patient to pay special attention to the increased risk of hypoglycemia due to aging. The third case is with bilateral adrenal aldosterone producing adenoma. Since this patient is with this condition, DeepDR LLM will recommend this patient to continue to take spironolactone to control the blood pressure. The fourth case is with the elevated level of low-density lipoprotein cholesterol. DeepDR LLM will recommend that to prevent cardiovascular disease, a patient should take moderate intensity statins and also give the matters needing attention after taking statins. To evaluate the patient outcome after integrating the DeepDR LLM system into primary care workflows, we also conducted a real-world prospective study, and this is the overall study design. Overall, we have conducted 2 sub-studies to investigate the impact of DeepDR LLM on patient outcomes. The first sub-study is targeting at patients with newly diagnosed diabetes. We evaluated the diabetes self-management behaviors. And the second sub-study is targeting at patients with referable diabetic retinopathy. We assessed whether they attended ophthalmologist appointment in 2 weeks. This figure shows the detailed study design. For sub-study 1, we follow up the participant at 2 weeks and 4 weeks to evaluate their status of diabetes management using questionnaires. For participants in sub-study 2, we investigated at 2 weeks follow-up to evaluate their referral rate and time to ophthalmology department. And this figure is a flow diagram illustrating the screening, selection, and management of study participants. This table shows analysis of study outcomes in 2 sub-studies. As you can see, that participants in the DeepDR LLM arm show better self-management and referral behaviors. We also conducted post-deployment evaluations to assess the quality and level of emphasis of the management recommendations generated by DeepDR LLM. And as you can see in the right figure, integrating DeepDR LLM enhanced the quality and perceived empathy of the primary care physician's management recommendations. Furthermore, we assessed the primary care physicians' perceptions and satisfaction towards our DeepDR LLM system. And as this table demonstrates, most of the primary care physicians deem the DeepDR LLM system simple and understandable, effective, and safe. After the integration of DeepDR LLM into the clinical workflows of primary diabetes care, it could assist primary care physicians in detecting diabetic retinopathy and generating reliable and evidence-based management recommendations for people with diabetes. Finally, I would like to thank all the participants and investigators of this study. Thank you very much for your listening.
Patrick, any questions? I think last 2-3 talks we had continuous talks, and any questions are there, or anybody has any comments to make?
So I think there was a question which was came on the Zoom portal that let's presume in the near future AI and MI, that means machine intelligence, become a strong enabler to doctors where it becomes reliable and dependable. Does it mean that the entire study curriculum in the structure of medicine, not just ophthalmology, is going to see a sea change in the way we learn the medical profession?
Yeah, I think Professor Ben will answer this because we are on the brink of another study of medical education. You want to share something? They want to know, do you feel it will have a role in education, medical education?
Yeah, thank you. I think this is very good question. I think because of the event of the large language model and the foundation model, so now we see that the so everyone talk about AGI or clinical AGI. So we probably will see a very powerful, very knowledgeable AI teacher, AI professor, and not just in the medicine, but also I think for every, even in computer science, I think maybe I'm the maybe the first batch of the teachers will be out of date. Yeah, so compared with the AI teacher. So so I think of course the education will be changed by AI. But I think very important is what is the final objective to train or to educate the medical student to become what kind of doctor in future. I think, for example, now we maybe after 10 years in computer science, maybe the programmer is using this, and I think all the programming will be made by the AI. So what is the future of the student in computer science department? I think that is a problem. And I also discuss because I'm the actually the research from the computer science. But I think in medical, in ophthalmology, I think still we have some very important area. I think the human should have its own value. And for example, the creativity and the some like the disease, how to actually finally to find the solution or find the drug or new surgery or new treatment. So this is kind of a knowledge discovery. And I think at the current stage, the AI cannot actually teach or find the best solution in those domain. And I think to how to educate, how to cultivate the students' creativity and some scientific thinking, and also the basic how to say yeah, some like not just knowledge, but also how to create knowledge. I think this kind of ability is very important. And for the another is about some like the physical operation, and I think this is also the AI cannot easily to replace the student or doctors, and I think this is also very important. Our human teacher or human student can have a better learn from the humans expertise. But for other like other domain, like the some like the diagnosis, some like the prediction. So I think we can probably to make the AI teacher or make the AI like the colleague to help the doctor or the medical student better. I think that probably will be the future trends of the AI education and also in the AI in the ophthalmology. Thank you.
Thank you, Professor Ben. I think if we don't have any question, I have a small few 4-5 slides which will give you the gist of what we learned today. 1 minute. Can you see the screen?
Yes, we can see.
One minute. I think thanks all of you for being for this webinar, and it was really great. And one question which comes to all of us as a clinician, why as clinician we need to know all this? Because we are treating patients, dealing every day with so much stress of surgery, talking to patients. Why we need AI now? I have some of the reasons why. So I tried doing the search on PubMed, trying to see that if we look at what are the articles related to AI, machine learning, and neural networks, retinal diseases in last 6 months, there are 564 articles. And we all today practice evidence-based practice. So you cannot ignore this 600 based articles which have come now, and they will definitely find a place in our clinical management, clinical care. And we need to understand these articles. To understand this, you need definitely some basic terminologies, know the concepts, what exactly these terminologies and how these have been used in diseases or in ophthalmology is something, and this webinar was mainly talking about it. We also seen that the AI algorithms can analyze imaging data, probably matching or sometimes exceeding the human performance, and it can detect many of these diseases. Definitely that has a potential to improve our patient care. As we saw that it can predict the progression, treatment response, we can have a more personalized treatment strategy. Probably we can optimize the therapy for our patients. It is augmenting the clinical workflow. Definitely it can be integrated, as we saw, with the EMR, coding, appointment scheduling, and definitely where it has really created a dent is the screening programs. In ophthalmology, diabetic retinopathy screening stands one of the very important disease, and it has really shown, and that's the reason it is already incorporated into many of the guidelines. Many of the commercial cameras now have a AI integrated solution within it. Definitely it can optimize the clinical workflow. Another important is many times we need to know these because we tend to get answers to our questions, our challenges. Like a challenge that can we know whether a OCT will respond to a treatment or not. And this, as an ophthalmologist alone, we cannot do. We need to collaborate with data scientists, researchers, technologists, basically a crosstalk, and really creating what we call as a translational research. We can also contribute to AI development. We may not be a developer, but clinician inputs are very, very important. I still remember the initial Google project labeling those images and understand. We really didn't know what deep learning is all about, but we can definitely contribute to the AI development. We can evaluate these tools. Many of these tools which come to clinical practice, we want to know, because when they develop it, unfortunately, many of these tools, they don't think that how it would be used in a clinical settings. And I think we have to answer these questions when we try to use and evaluate these tools. And that can only be there when you get involved in these studies which are related to AI. And finally, the ethical and medical legal awareness. Accountability finally is for the clinician. And we are responsible for what happens to our patient. And until we are convinced that this solution works, we can never have a patient trust, because he has, at some stage, there will be AI-driven decisions, and he will have a trust only once a clinician has trust in these. So definitely one of the things which this webinar is all aimed is towards practicing ethical and responsible AI. Thank you very much. I'd like to thank my team. Dr. Namrata, your final comments.
Thank you. I think, Dr. Rajiv, this was a very, very useful resource as far as artificial intelligence in ophthalmology is concerned. And the momentum of the entire talks, right from the basic till whatever has happened up till now in diabetic retinopathy, I think that crescendo really, congratulations to you, Rajiv, for keeping that crescendo, because right from the beginning till the end, I think everybody would become aware of what is artificial intelligence in ophthalmology and how it is translating into our clinical practice. It is here to stay. And we had some very excellent talks by all the presenters. I would like to thank all the presenters for the same, and particularly you for carving it and being the architect of the whole program.
Sure.
Thank you. I think it was very, very useful.
Thank you.
Thank you so much, everyone. And we would also like to thank our audiovisual team headed by Mr. Sunil, as well as our AIOSSC Scientific Committee team, Mr. Bhupinder Surinder, for helping this. Thank you so much. Thank you.
Thank you.